Hello, everyone. Welcome back to our video series on daily earthquakes. On this video, I'm not going to really talk about any particular earthquake, but I would like to give you an idea of a very important thing that we do, and that has to do with the locating an epicenter for a given event. Okay, remember that we use wave for our studies. So when a rupture occurs, there are two principal waves that are generated. The P wave, compressional or pressure wave, they are the fastest type of wave that we have in rocks. And we have then what we call the S wave or shear wave. These are the propagation of shear energy, and they are slower. Usually, some people use P for primary and S for secondary wave, but actually they are pressure and shear type of wave. Now, because they have a different velocity of propagation, they will travel at different speeds, and as they go farther, the separation in time between the arrival of P and S will change, will increase. Well, that idea is that exactly what we're going to use to try to locate the epicenter. Okay. Remember, we don't know the location, we don't know the time, the exact time of the rupture, but we're going to measure the times of propagation. So we will take the P wave time as the basics. We will call it a zero reference point, and then we will look for the difference between that point and the S wave arrival. And that will be the information we're going to use to try to locate the position of the first perturbation. For that, we need at least three locations. That's the basic that we're going to be talking about, very basic idea. These through the years have been improved quite a lot, and these processes are almost automatic now with so many stations around the world. What I will show you here is a very basic principle. So we need different stations at different distances, and then we will triangulate the uh, times that take from P and S wave to arrive at those specific positions. We will do this example using a very simple and nice application called virtual earthquake. I will recommend that page for most of you. I will put the link at the end of the comments, and I'll get back to that to show you with a very simple example how we try to locate the epicenter of an earthquake. Okay, so with that, let's get to the page of virtual earthquake. And of course, the first thing we see are seismograms, they are records. We have been looking at those daily on different earthquakes. The record shows a lot of movement, events. There is a video that I recommend that shows a little bit about that. So we have what we call the body wave traveling, and we have the P wave and the S wave. Remember, those are going to be the ones we're going to be using. But there are other things that shows on the records. Reflections from the core, reflections from the mantle, the outer core, the inner core, a lot of data. And then we also have the surface wave that travel along the surface. But for this particular video, we are interested in picking up the first arrival, that usually the P wave is the fastest, so nothing happened before that. And that's a good sign because that will give us the start of our analysis. And then we have to choose an S wave arrival because the difference in that time is the one that will bring some information for us to locate the epicenter. Okay, so this page is very interesting. It gives us the idea of the chance to play with some records. It has some different historical records you can play with. Since we have a very interesting earthquake yesterday, today is the 21st of December 2022. There was a nice, interesting earthquake offshore California. So let's try it in a San Francisco area earthquake. So we choose that on the page. It gave us a map with a lot of stations. The little dots are stations. The earthquakes is somewhere near San Francisco. So we have to locate it. In order to do that, we have to measure the difference in time between the arrival of the P wave and the S wave. And then we'll use travel time curve that through the years have been modeled. You see, we have a model of the Earth velocity field that comes from thousands of observations during all the digital recording history of seismograms, of earthquakes. Okay, so what we'll do is we need some records from different stations, and we have to pick the arrival times for the P and S wave events. So this is a station in Eureka, California, and we have to pick the P wave. So we'll see here like a little first break up, and that will be the zero. Remember, we're going to zero on the P arrival. We want to see the difference until the S arrival gets here. And for us, that will be about, if we pick it up here, it would be about 40, close to 50, but it's more like 48, 49 seconds. So our picking will be 49 seconds. Then we have zero for the P arrival, was picked on this first push up in the record. And then we'll pick the S somewhere around here, which is 72 seconds. And this is in a station in Elko, New Nevada, I think. Okay, and then we have Las Vegas station, and we have the P arrival here, and the S arrival is somewhere on here, which is at about 64.260, 64 is as close as we can get with this scale, I suppose. Okay, so now we have to look at the difference between P wave and S wave. There are tables that relates that different time to a distance. So now we have to choose that distance. Okay, so in Eureka, 49 seconds should give us, that's 49 right here, should give us a distance of about 479 kilometers. We're picking that right here. The Elko, Nevada is 72 seconds. So 72 seconds is right here. And that will give us a distance of about 680, 690 kilometers. Okay. And we're doing this really rough. The automatic picking right now by computers is much better. But I want to give you the idea of the procedure. Okay? So Las Vegas was 64 seconds, and that, according to the tables of velocity, should put us here at about 605 kilometers from whatever we are. Now, look at this is important thing. What we're picking is a distance from the place of the station to the epicenter. Now, we don't know where it is. It can be anywhere around a circle with a radius of 479 kilometers from Eureka, of 690 kilometers from Elko, and so on. Well, now we have to find the epicenter by triangulating. Okay? Why? Because there is a circle with given radius, but where all those circles collide, converge, that should be the place where the earthquake occurred, and we call that the epicenter. Okay? So this is the three distances given Eureka, radius, the Elko, and the Las Vegas type of circles, and they all should collapse or converge to this point. And that would be the place for the epicenter. Okay? So we actually did it very close. Okay? This is the place where the earthquake took place. Okay, so very simple uh, approach to picking up and finding the epicenter of an event. Again, nowadays there are so many stations, everything is computerized, and that's why it is so fast to make this calculation. It's almost automatic when records trigger on different places around the world. The red, the net is interconnected, and all these processes are almost automatic. So I hope with this to have given you an idea of how we work to locate the epicenters of different events around the world. Okay, so it's very interesting. Again, wave propagate through the earth. They arrive at different stations. We pick up those events and we can make a lot of calculations. Okay. There is a lot more in seismology. It's very interesting. Like how do we know the structure of the earth? How do we pick different events? But if I have time during the series, I will do something about that. For now, again, saludos por el mundo y gracias.